In chapter 2 and 3, we're going to be looking at systems of differential equations. For example, here's a system of two equations for two unknown functions. There's still only one variable t, so these are still ordinary differential equations. We're not going to talk about partial differential equations in here. Everything will be a function of just one variable, which we'll usually call t. But there are two unknown functions, x and y, and two equations. Normally you should have the same number of equations as unknowns. Just like for algebraic, linear or nonlinear algebraic equations, you should normally have the same number of equations as unknowns. Differential equations, normally the same number of equations as unknowns. So here are two equations for two unknowns. We're mostly in chapter 2 and 3 almost exclusively talking about systems of two equations, two unknowns, because it's pretty obvious what you do in the more general case when you have three equations and three unknowns and so forth. So let's look at a system of two equations, two unknowns. Well, normally the right-hand sides could be functions of t also, so f and g can be functions of the variable t as well as the two unknown functions. But if it's not, as here, if they're not functions of t, then this is an autonomous system of two equations, and we can qualitatively study this more. Now, we already saw in chapter 1 that even a single equation for one unknown function, it's very rare that you can actually solve it analytically, so we talked about numerical solutions on the computer and qualitative solutions. Well, with two equations, two unknowns, it's even more rare to be able to solve them, although we will actually solve some simple ones in section 4 of chapter 2. And in section 5, we'll talk about numerical methods, which is Euler's method, which is pretty obvious generalization of Euler's method for a single equation. But here in sections 1 and 2 and 3, we're going to talk about some qualitative methods, but these methods only work for autonomous problems, that is, where the right-hand sides do not involve the variable t. Now, for a general system where the right-hand sides do involve t, the equivalent of a slope field would actually be a three-dimensional plot, and you'd have to plot the slope as a function of x, y, and t, and that's almost impossible to visualize, so we won't even try to draw the equivalent of a slope field for systems of equations. But for autonomous systems, we can draw a phase plane, which is analogous to the phase line. And here's an example of a phase plane for this system of two equations, x prime equals minus x, y prime equals minus 2y. We can draw a phase plane here. This is x and y. There's no t-axis because there isn't any t on the right-hand side, so the direction of x prime and y prime doesn't depend on t. But see, if you take any point xy, for example, x equals 1, y equals 1, it's probably about there, then x prime, y prime would be minus 1, minus 2. In other words, the rate of change of x is minus 1, the rate of change of y is minus 2 at the point 1, 2. And so there's a arrow pointing in the direction of minus 1 comma minus 2. That's the direction that you'll go. So basically, if you ever end up here, you're going to go that way in terms of x and y now. So I know this looks like the slope field thing, but it's really the slope. It's the slope line equivalent of the phase line. It's the two-dimensional equivalent of the phase line. It only applies to autonomous problems. So it doesn't matter what t is. If you're ever at this point, x, y, the arrow tells you how x and y are changing. And notice they're all the same magnitude, just like the phase line. They don't bother trying to draw, whether it's going up fast or slow. They just show which direction it's going. On the phase plane, they also don't try to show how fast it's going in any direction. They just show which direction in the xy plane it's going. But this gives you a good idea of what the solutions are going to do, because they'll just follow the arrows. Words, if x comma y, if the two unknowns x comma y are, whatever this is, 1, 1, then it's going to go in this direction. It doesn't matter what t is. And of course, the DE Tools has an app for that. It's called HPG System Solver. And let's look at differential equation. X prime is equal to x squared minus y squared, and y prime is x times y minus 4. This is an autonomous system of two equations. There's no t on the right hand side, otherwise we couldn't use this app. And let's show the field. And if you take any point xy, for example, if x and y are 0, x prime is 0, y prime is minus 4. So if you're ever at the point 0, 0, you're going in the direction of the vector 0, minus 4. In other words, x doesn't change and y is going down. So there's an arrow or close to there that's just showing going down. So these arrows, notice the magnitudes are the same. They don't try to show how fast it's going. It doesn't matter. Just follow the arrows. Wherever you start, you go in the direction, because whatever x and y is there, this tells you how x and y are changing, how fast what direction they're changing. Now, the phase lines, you had equilibrium points, and some equilibrium points were sources, and some were sinks, and some were nodes. Well, a little more interesting things can happen here, but we still have equilibrium points for autonomous problems, and not if there's a t on the right hand side, but autonomous problems, you can still talk about equilibrium points. Those are points where both x prime and y prime are 0. In other words, set both of these equal to 0. X squared minus y squared equals 0. X squared minus x times y minus 4 equals 0. And well, x squared equals y squared means x is plus or minus y. If y is minus x, that's impossible. This can't be 0. That'll be minus x squared minus 4. If y is x, then x squared minus 4 is 0, and x is plus or minus 2, in which case y is plus or minus 2. So if we set both of these 0, we get two equilibrium points. There's 2, 2 and minus 2, minus 2. Both of those sets of values of x and y will make both x prime and y prime 0. It doesn't do any good to make one of them 0. If the other's changing, it's not going to stay put. But if you start at 2, 2, exactly 2, 2, you'll stay there. For example, let's start exactly at 2, 2 and see what happens. And they stay there. There's the point right there. So we're starting exactly at that point. We're going to stay there. If we start at minus 2, minus 2, that's the other equilibrium point. We're going to stay there. But what if we start close to one of the equilibrium points? So those are the equilibrium points for the two-dimensional case. What if we start close to it? Well, let's pick a point close to this equilibrium point, minus 2, and it gets sucked into it. We try different starting points. Looks like no matter where we start, near minus 2 gets sucked in. So we're suspecting this should be a sink. And actually, we won't be able to prove anything about whether these are sources or sinks, or even define what that means until chapter 5. We won't be able to prove that these are sinks. That's a sink, but that's in chapter 5. But for now, we're just doing the experiment here, and we're minus 2. If you start exactly there, you stay there. If you start near there, it looks like you're getting sucked into it. Now, if you start near the other equilibrium point, 2, 2, it looks like you get blown away. If you start exactly there, you'll stay there, but it's a unstable equilibrium point. A source is an unstable equilibrium point. Notice this one gets blown away and then eventually gets sucked into the other one. So this looks like a source, because if you start anywhere close to it, you get blown away. If you start anywhere close to this one, you get sucked in. So this looks like a sink. That looks like a source, at least experimentally. We'll confirm that this is a source, and this is a sink in chapter 5 analytically. Now let's look at another example in section 2.1. It's a predator-prey problem. R is the number of rabbits, F is the number of foxes. And to understand the model here, let's suppose dr dt was equal to 0.1 times r. What would that mean? That means that the rabbits are going to increase at the rate of 10% per year or day or whatever the time unit is. Let's say day. So they increase 10% per day. But now, see, if you factor out an r here, the right-hand side, you have r times 2 minus 1.2 f. Well, you can think of that other factor, the 2 minus 1.2 f, as being the rate of population increase of the rabbits, because dr dt is r times that factor. And you see, the more foxes there are, the smaller the rate of increase. If there's no foxes, then the rate of increase is 200% a day, I guess. Factor out an r, the more foxes there are, the lower that 2 becomes. It's r times 2 minus 1.2 f. So you have more foxes, the rabbit increase rate is lower, which is reasonable. And at some point, the rabbit increase rate gets to 0 and then goes negative. If you have enough foxes, the number of rabbits goes down. And similarly with the foxes, if you factor out an f here, you have f prime is equal to f times minus 1 plus 0.9r, and you can think of the minus 1 plus 0.9r as the rate of increase of foxes, because that's multiplied by f. And you see now that if r is 0, it's negative 1, which means if there's no rabbits, the foxes decline, whereas up here we saw if there's no foxes, the rabbits like that just fine, they increase. But the foxes don't like it when there's no rabbits, they decrease. The more rabbits there are, the less negative that rate of increase is. So at some point you get enough rabbits, the foxes actually increase. So that's kind of what's going on here. Anyway, it's an autonomous system of 2 equations, 2 unknowns. You can plot the phase plane, and let's do that. Okay, so here's our predator-prey system. For this app, we have to call the variables x and y instead of r and f. So x represents the number of rabbits, y is the number of foxes. And notice I factored out the x or the r here, so you can see what I was saying, that the rate of change of rabbits is basically, this is it's not a constant anymore, but it's the proportionality constant. The bigger this is, the faster rabbits increase. The more negative it is, the faster they decrease. It's kind of like the percentage rate of increase. And as you can see, if there's 0 foxes, the rate is 2. The more foxes there are, the lower the rate is, and it eventually goes negative for big enough y. On the other hand, the foxes, their rate is minus 1. They're decreasing if there's no rabbits. The more rabbits there are, the less negative and eventually positive the rate of foxes goes, which all kind of makes sense. And so if we start from a given number of rabbits and foxes, so that this is a system of 2 equations, 2 unknowns, we need 2 initial conditions. We need to know x and y at t equals 0, and let's just click on a point here, and that will be our starting value. Well, we can type it in here. Let's start with 1 rabbit and 1 fox. Well, of course, 1,000 rabbits, 1,000 foxes, presumably. We don't want half of a rabbit here. So start with 1, 1 and see what happens. That's whatever the units are, thousands of rabbits, thousands of foxes, whatever. And so we started right about here, and the interesting thing is it goes in the cycle here. And it kind of makes sense if you think about it. At this point, remember the x is the rabbits and y is foxes. So the rabbits are increasing, and you get enough rabbits, and the foxes increase because they got lots to eat. So the foxes increase, the y is going up, and y keeps going up. But at some point, there's enough foxes that the rabbits start going down. X is going down, and then you've got enough foxes here. Well, the rabbits keep going down. And then there's so few rabbits now that so few foxes now that the rabbits start to increase, and so it goes in a cycle. And let's start at another point, and it's another different cycle depending on what you start with. So it looks like whatever you start with, you're going to go in some cycle, which is interesting. So a lot more interesting things can happen in two variable problem than one variable. One variable is either going up or down, and you've got sources and sinks. Here you don't seem to have any sources or sink. There's an equilibrium point here. This is let's see, this is the point where both of these are zero. Like that would be y is 2 over 1.2 and x is 1 over 0.9, so x is about 1.11 is the equilibrium point, and y equals 2 over, that's 1 2/3, 1.67 I guess. So that should be an equilibrium point. If you start at that point, you should stay there. And yeah, there it is. See, there's the equilibrium point. So if you start there, you stay there. Start anywhere else, you kind of circle around it. So can't really call that a source or a sink. We'll see other examples where equilibrium points are not sources or sinks. They're, you get sucked in from some directions and blown out from other directions, or like here, it just circles around their center. So a number of interesting things can happen. But this is the phase plane, which is the equivalent, two-dimensional equivalent of the phase line, and it only works for autonomous problems. But there are a lot of interesting autonomous problems, like the predator-prey problems. And by the way, problem 7 is another predator-prey problem, a little more complicated model. And the equilibrium point here looks like a sink, but something we're going to call later a spiral sink. In other words, if you start basically anywhere here, you get sucked into it, but you spiral as you go in instead of just going directly there. And I've given you problems 1 through 6 in section 2.1. These refer to two different predator-prey systems. And I would advise factoring out a y out of this equation and an x out of that. And I believe both of them, y is the predator and x is the prey. I have to check that, but well, you can check by saying, well, what if, if x is 0, y is decreasing, so it must be the predator. If there's no prey, then the predators decrease. Whereas if y is 0, x increases, well, at least up to a certain point. This has built into the model that if they get too many rabbits, they start dying off because there's not enough lettuce or something. But as long as x is small, if there's no y, then x increases. If there's no x, y decreases, so y must be the predator because it doesn't like it when the other species is gone. The x must be the prey because it does like it when the other species is gone. And I guess it's the same thing here. You're supposed to find all equilibrium points for the two systems. So you set, for one, you set both of these equal to 0 and factor things out and find all the equilibrium points. The positive ones are the only ones of interest. Non-negative ones are only ones of interest, but find them all. And then they say, well, suppose the predators are extinct, then show that the predators stay extinct. So if y is ever 0, then dy dt is 0. So if any, doesn't matter how many x there are, if y is ever 0, it stays. So extinct is forever. You can also see that if x is 0, it stays extinct. So if there are no rabbits, there'll never be any rabbits. That's what you would hope the model would say. If it doesn't, something's wrong. But the foxes, well, one of your problems is to say what happens to the foxes or the y if the rabbits disappear, or what happens to the rabbits if the foxes disappear. So if you, for example, what happens to x if y disappears? So if y is 0, it'll stay 0, and that term will disappear. And then you've got just a single equation and a single unknown. So this is basically a chapter 1 problem now. And you can draw the phase line for it and see what happens qualitatively. Even though you can't solve it, you can see what happens to the rabbits if the foxes are extinct, or you can see what happens to the foxes if the rabbits are extinct. And there's one of their famous matching problems in section 2.2, problem 11. They've got 4 phase planes drawn and 8 possible equations. You're supposed to match them. For example, A, which one of those 8 could have this as its phase plane? And there are various ways of doing this, but I would look for equilibrium points to eliminate possibilities. And if you look at this, it looks like there are equilibrium points at 0, -1, that is x equals -1, 0, x equals -1, y equals 0, and it looks like there's one at 1, 0 also, and it looks like those are the only equilibrium points. This one looks like a sink, it's sucking everything in. This one actually looks like kind of a node. It's you know, if you, in one direction you're getting blown out, in one direction you're getting sucked in, but it's still an equilibrium point. So we're looking for systems that have equilibrium points at -1, 0, and 1, 0. And 2 and 7 both have equilibrium points at y equals 0. When y is 0, the second equation right inside is 0. When x is plus or minus 1. So it looks like it's got to be either 2 or 7. And how can you tell the difference? The only difference is when you have a minus y here. So pick a point where y is, say, 1. Say x equals 1, y equals 1. Then that looks like about here. It looks like x prime, y prime would be 0, comma, minus something. So if x and y are 1, that would be 0, that'd be -1, this would be 0, and they'd be +1. So this must be the correct one, because it correctly predicts that at 1, 1, it'd be going down. So this would be pretty hard if you had to actually figure out what the equation was for this, but you can eliminate other possibilities, and it must be 7.